So what I'm going to do next is that I want to talk about a special case under the Solow model, which is without population growth. So remember that in our previous discussion, we talked about the case that is the economy is with population growth. And then we look at the Solow model. Now we want to look at the Solow model again, but we assume that there is no population growth. And then we want to see how will that change the results of the way we solve the model and the answers. It turned out that the way we solve for the model are exactly the same. The answer is slightly different, but it probably is more intuitive. So now let's go through this special case. So again, we need to set up the Solow model. We have the equation describing the household decision, which is that we save a portion of our income. We also have the equation to characterize the firm's behavior, which is the production process. We adopt the Cobb-Douglas production function. We have an equation to characterize how does the capital evolve over time, and in here we adopt the law of motion. At the end, we have an equation characterize the equilibrium of the economy, which is that whatever amount of goods that is produced need to be either consumed or invested. So obviously, the setup of the Solow model are exactly the same as the earlier case. Now let's move on to look at the computational details. We said that we want to focus on the per capita variable, so then we define the aggregated variable, and then we define the per capita variable, and then we divide the variable by the population size, and then we have the per capita variable. Same thing. And then we need to convert the system equation above from the aggregated variable to the per capita variable. So then here's how we do the conversions. Same thing here. When we divide both sides of the equation by nt, we then successfully converted the equation 1 into equation 1 plum. That is the ct equal 1 minus delta yt. Nothing to do with the population changes. For the second equation, we do the same thing. Again, we are going to have yt equal a multiply the kt to the power of theta. Again, not be affected by whether or not the population size changes. Now, for the first equation, again, we divide both sides of the equation by nt. We are going to have the total output per capita equal the total consumption per capita plus the total investment per capita. Again, nothing got changed. How about for the third equation? We said that the third equation tells us how does the capital evolve over time. So then when we divide both sides of the equation by nt, then we are going to have 1 plus n multiplied by kt plus 1 equal 1 minus delta kt plus the it. So the relationship of the law of motion still holds when we express everything in terms of per capita in equation 3 plum. However, now you say, hey, wait a minute. In here, we do not have population growth. Therefore, the n need to be equal 0. So we need to cross this term out. In other words, when we are looking at kt plus 1 over nt, we still need to separate out into kt plus 1 divided by nt plus 1 multiplied by nt plus 1 over nt. But in here, because the nt plus 1 and the nt are exactly the same, therefore it crosses out. So then, given that the population growth rate is 0, so then we can cross it out. It no longer exists. So now, because we drop off the n, then the equation for the law of motion in aggregated term and in per capita term now look exactly the same. That's the main difference of the case of the model with no population growth versus the model with population growth. So after we successfully converted all the equations that expressed at the aggregated term into the per capita term, now we want to solve for it. So the problem that we want to solve for now is this equation in here, but we can cross out the 1 plus n in here. And then the all the motion of the economy remain the same. Once we know the k, we are going to have all the values for y, c, and I, and then we know the k next period. So then same thing for here, that the economy will be able to be in the steady state. And when we want to come up with the steady state condition, the equation now we are looking at is the kt plus 1 equal 1 minus delta kt plus the it. So then the new equation here need to cross out the 1 plus n, and then we cross out all the n. So the steady state condition now becomes it equals delta kt. So you say, hey, now this is more intuitive. That is because we say if the economy wants to have the capital stock stay at the same level, we want to have our investment exactly equal to the wear out of the capital stock. And then the capital stock level will stay the same. In the earlier version of the model, given that the population grows over time, so then to adjust for the population growth, we need to have an n plus delta multiplied by the kt. It may not be that intuitive why the steady state condition equals it equal n plus delta kt. However, in here, when there is no population growth, now this equation for the steady state condition is more intuitive. For the economy to have the same level of k over time, the new investment need to equal the depreciated capital stock. So when we want to solve for the k steady state for the Solow model under the Solow diagram, we have a new steady state condition. That is, when we want to keep the capital stock at the same level, then the it need to be equal delta kt. And then when we draw the Solow diagram, the only thing that got changed is the steady state condition. Other than that, all the lines remain the same. We have yt equal akt theta. We have it equal s delta yt, which is the combination of the household decision related to consumption and saving, and the equilibrium condition that related to whatever amounts of the output that is produced need to be either consumed or invested. And then we know if we want to find out the steady state of the economy, then we need to find a point where the actual investment equal the investment required to stay at the same level of the k. It turned out to be the k highlighted in the diagram. And then we know that under this graph, the portion in A is related to consumption, the portion in B is related to investment, and the portion of the A plus B will be the output. And then we also say that we can solve for the steady state numerically. When solving the steady state numerically, we focus on the steady state condition and the equilibrium condition. And then the only difference of this special case versus our earlier one is that now we don't have n, so we cross out the n. So in the steady state condition, the it equal delta k, the equilibrium condition remain the same. So then when we rearrange the equation, then we are going to have the delta kt equal s delta a kt to the power of theta. Then we rearrange the equation. We are going to solve for the k steady state. Now the k steady state equal s delta multiplied by a divided by delta, the whole thing to the power of 1 over 1 minus theta. So here we review how we come up with the k steady state for the Solow model based on the Solow diagram and based on the equations. But in here, we are using the special case that there is no population growth. And I hope that up to this point, you are familiar with about how to solve for the Solow model, especially for how to come up with the steady state for the Solow model.